discuss agriculture hydroponic system scenario. A startup in Rwanda introducing hydroponic farming to address land scarcity and improve food security. The system will manage data on the hydroponic setup, nutrient solution, crop growth stage, water usage, and harvest record. Farmers can access the system to monitor and optimize their setup. Part 1. Assess functional and non-functional requirement. First one, functional requirement. Identify and define the core functionality of the system tailored to assign it scenario. Ensure functionality include the data storage, retrieval, reporting, and integration with relevant technology. Second one, non-functional requirement. Define the system performance, scalability, security, reliability, and usability requirement. Consider sector-specific non-functional requirements such as real-time data processing for IoT or blockchain transparency. Part 2. Design the database model. Conceptual model. Identify the key entities, attributes, and relationship in the system. Define the relationship. Create a conceptual model. Second, logical model. Normalize the conceptual model into logical schemas with tablet and relationship. Define primary and foreign key for the tables and establish relationship between them. Ensure data redundancy is minimized while maintaining integrity. Third one, physical model. Map the logical model to a specific database management system. Define the tablet structure. Define the table structure. Include the data type.
For hydroponic system setup, ability to store information about each farmer's hydroponic system such as system type, location, and size. Nutrient solution. Store the record of nutrient composition, amount used, and frequency of change. Crop growth stage. Store the detail about crop types, growth stages, and crop permanent. Water usage. The track daily and historical water consumption per system. Harvest record. Log harvest date, yields, and crop quality data. The report. Reporting. Generate the report on water usage, nutrient consumption, crop growth, yield, prediction, and harvest history. Provide insight and recommendation based on historical data, example trend in water usage, nutrient needed, and different growth storage. Farmers should be able to export the report for analysis or sharing with stakeholders. The real-time data monitoring. Integration with IoT sensors to monitor the real time of data, example, temperature, humidity, pH level, and water flow rates. Alert when the certain shows, example, water level, nutrient consumption are extended or fell short, promoting action. Integration with external technology. IoT integration for real-time monitoring. Potential integration with mobile app for easy access and notifications. Integration with weather, IPS, and adjust nutrient and water solution based on external condition. Integration with marketplace for selling surplus crops. User management. Different access level, farmer system administrator support. Ability to manage user profiles and preference. Analysis and recommendation. The data for optimizing nutrient levels
in crop condition, water levels or nutrient imbalance. Response time. Queries, example reporting or monitoring, should be completed within a few seconds to ensure a smooth user experience. Second is scalability. The system should be able to handle a growing number of users, sensor data, and farms as the number of farmers using hydroponic in Rwanda increases. Others is horizontal scaling. The system should support adding more servers or resources as data or user load grows. Third and functional requirement is security. Security includes data protection, means all user data, example, personal details, farmer data, must be securely stored and encrypted both at rest and in transit. And authentication, this is other security. Implement multi-factor authentication or MFA to ensure only authorized user can access sensitive data. Secondary is access control. Ensure proper role-based access control. In other words, is RBAC. That helps to manage different levels of access. Third and functional requirement is reliability. Reliability includes the systems must higher available with minimal downtime or target available 99.9% or higher. Backup and recovery. Implement regular backup procedures to prevent data loss and ensure quick recovery in case of failure. Fifth and functional requirement is usability. Usability includes the system should have any intuitive and user-friendly interface, even for users with limited technical knowledge. Others is support for multiple languages considered Rwanda's multilingual context, example Kinyarwanda, French and English. Mobile friendly design for easy of access in rural areas. Other non-functional requirement is sector specific requirement that include the real-time monitoring, means integrated with IoT device for continuous tracking of crops, water and nutrient level. Secondly, data transparent. Blockchain or secure ledger technology may be implemented for transparent tracking.
Farmer represent the user farmer of the hydroponic. We have hydroponic system as another entity represent the setup of system used for hydroponic farming, and also we have crops represent the crops grow in hydroponic system. We have nutrient solution represent the nutrient solution used for crop growth, and also we have water usage represent water consumption for each hydroponic system, and also the latest entity have harvest record represent the harvest data for the crop grow. And also we have the diagram that show those entity and those relationship. We have the first entity such as nutrient solution that contain these attributes. We have nutrient ID as primary key, nutrient consumption, nutrient amount and the frequency. And also we have the water usage that contain these attributes, water ID as primary key, water consumption and resources. And also we have another entity such as harvest record that contain those attributes such as harvest ID as primary key, yield quantity, date and qualities. And also we have farmer as another entity that have an attribute farmer ID as primary key, farmer name and phone number. Also we have crop grow as another entity entity that has an attribute crop ID as primary key, system ID as foreign key, and also season. And the latest entity that we have is hydroponic system that contain these attributes: system ID as primary key, system type, farmer ID as foreign key, and location and size. Also we have the relationship between those entities. One farmer has many hydroponic system, and they also one hydroponic system as an entity has many crops as another entities. Hydroponic system have many nutrient system, and also hydroponic system has many water usage, and also crops has.
The entity will have such attributes like system ID as primary key, farmer ID as foreign key, system type, location, size. For crops, also we have crop ID, system ID as foreign key from system table, crop type, planting type, growth stage, expected yield. Nutrient solution as another entity with nutrient ID as primary key as attribute, system ID as foreign key, solution type, composition, amount, used, date, mixed. For water usage, you have usage ID as primary key, system ID as foreign key, date, water that were consumed. Harvest liquids, we have harvest ID as primary key, crop ID as foreign key, harvest date, yield, quantity, and quality. Second, we have those keys. Let me explain to you. First one is the primary key that uniquely identify column from each table. The second is like foreign key, which link related tables, ensuring referential integrity between entities. Also, we have our entity relationship diagram, which is going to show us all entities that consist in our database. First, as you see, we have entity number 1, which called hydroponic system. This entity is respectively related to farmers which have one-to-many relationship and all those attributes as we have seen in the above. Also, the second one will be farmers which is connected to harvest report, and it is many-to-many relationship because many farmers can produce many harvest, and as you see, those are attributes of farmers and of harvest report. Also, harvest report will obtain nutrient solution, which will handle the problem of nutrients in a mill or a branched mill. Also, harvest report can obtain many nutrient solution as a relationship. Also, nutrient solution will be matched to water usage. Water usage can assist many nutrient solution. That's why we have many-to-many relationship. Also, water usage can provide crop growth, many crop growth from many water usage. That's why we have many-to-many relationship. This is how our entity relationship diagram will look like.
We would focus on implementation specific in the database management system. Database management system use relational database like Postgre, SQL, and MySQL. DADES. Index. Create index on frequently required columns such as system ID, crop ID, harvest, date, and date mixed for fast lookup and reporting. Partitioning. Partition large tables such as water usage and harvest record by date or system ID for better query performance on a large data set. Constraint. Implement constraint for the data validation. Example, check constraint on water consumption to ensure valid value or on the expected yield for crops. Data type. Use appropriate data type like INT for ID, varchar for text field, data for date related field, and decimal for numerical field with price value, example, amount used, and water consumed.
Relationship diagram from draw input output application. As you see, we have attributes as water ID as primary key resources which can be optimized or can be edited. As you see, this is where our group member called Mugisha have created those entity relationship diagrams. As you see, it is very simple to create those creations because we have this application. This is the first one, entity relationship diagram. Also, you have seen this conceptual model diagram which shows the relationships among our database entities. So we can use those objects to design our graphical drawing as